Hello everyone. Today I will talk on partial differential equation. So this will be respect to partial x, partial y, or partial z. Okay, or you can have any other variables. Okay, compared to just a recap, ODE, ordinary differential equation. So you have d dx. Okay, so this is only 1D. And this is 2D and above. Okay, all right. We will try to look at problem on steady state temperature in a rectangular plate. So maybe let's look at this as a rectangular plate respect to x and y. So you have a two-dimensional system. This plate have a size of L. Okay, let's assume size of L. And you can have a temperature over here and also temperature over here, and also on the side of the plate you can have some temperature reading. If you are looking at a steady state temperature, means that does not change over time. By right, you are trying to solve Laplacians or Laplace equation. Okay, this is the form of Laplace equations, but instead of u, you use t because the solutions give you the temperature. Now because it's in two dimensions, so you have one here. The first term is partial square t over partial x square, and then partial square t over partial y square. You have two terms because of the plate. Okay, that is the relationship. So I call this equation 1, and then usually what we will do, the solutions we take will in terms of the form equation 2. Okay, so here is the solutions in 2D, but as I mentioned in our class, this is actually equivalent to a multiplications of two one-dimensional function, one respect to functions x and another one respect to functions of y. I denote this as f1x and f2y. Okay, so I drop down this part. Okay, so I use this notation. It's just the same thing. So what we do next is we want to, so the aim to separate the equation, separate equation 1, and you get ODE, and eventually you get the solution. So usually it's a general solution, so you have some options. Okay, we will arrive at the general solution. Now let's move on. You substitute equation 1 into equation equation 2 into equation 1. All right, so what you do, you substitute t respect to f1 x and f2y. Okay, just substitute like this. All right, and then we will try to analyze like the following. Okay, so you look at the denominator. The first one here is respect change over x, and here respect to the change of y. So your functions 2 is something like a constant. Okay, so you can just do that, f1x over fx2, and then you have f2y, and then you have f1x, 2 equals to 0. At this point, you divide by equation 2, or you divide by f1x, f2y. So you have f2y divide with f1x, f2y the functions of fx, x square, plus f1x, f1x, f2y, partial f2y, y squared equals to 0. Now what do you see here? You can cancel some of the constant. For example, f2, f2, f1, f1. So you end up with, I drop down f1 fx, f2 1x over partial square plus 1 over f2y partial 2 f2y partial y squared equals to 0. So now what do you see? So you see you have separate these term only respect to x, and these term only with respect to y. So you have separate the equation. So what does that mean? It is safe to write f df dx square equals to minus 1 over f2 df2 dy squared equals to 0, but then you cannot equals to 0 because you have rearranged them by right. Since this is equal, that they should be equals to some constant. If these two are equal, they should be equals to some constant. This is the way we used to do things, okay? So the way we do it is 1 over f1 d square dx square equals to, maybe I choose minus k. Another one, I have 1 over f2 d2 f2 dx, sorry, dy square equals to minus k. So minus minus, you have a positive. Sometimes it is very common, okay, conventional to take the constant minus k, okay, because it depends to your solutions, okay. It's either actually. You can stick with positive if you want, but the important part, let's look at the solutions over here, okay. So the solutions over here, we try to find the roots, okay. So take d dx square equals to d square. So finding roots of d. So d square equals to minus k f1. So your d square is what? Sorry, if your d square is that, your d is dx is d. So you don't have f1 anymore. So it's equivalent to k. So your d square is, I just solve this, okay. So your d is square root minus k. We've done this in class, right? So this means this is I square root k, okay. So this is a complex roots. So the solutions is what? The solutions to your functions of x is a cos kx plus b sine kx, okay. Similarly, you works for this one, f2, or you can do d square equals to k, and your d is plus minus k, and this is distinct root. So if your distinct root, your solutions for y is a exponential ky plus b exponential minus ky. Therefore, your general solution to this steady state temperature in rectangular plate from equation 1 is written as, so if you have fx1, f2y, this is equivalent to txy, is cos sine, and then you have e ky, sorry, x here, e minus ky. So why I wrote down like this? So next one needs to use of the boundary conditions to find the specific solution. So boundary where? Boundary of your plate. Okay, what is this T? Do you have T not T after L? Okay, and we don't cover that here. So the objective is to arrive at the general solutions. Okay, thank you.